Hello everyone and welcome back. In this lecture, we're going to be working through the documentation example for K-means clustering. So pay close attention to how we don't need the actual label column, which makes sense because we're doing clustering, which is an unsupervised learning algorithm. Now the documentation's example is a bit peculiar in its choice of a data set. They basically have a really small data set and they actually do provide you with the label columns, which are unnecessary. So we're going to explain that along the way, and hopefully our own custom code along will clarify things further in the next lecture. But for now, let's get started, open up a new Jupyter notebook, and walk through the documentation's own example of K-means clustering. Alright, so I've started a new notebook, and as a quick note, you can find all the code that I'm going to be working through at this notebook right here, clusteringcodeexample.ipynb. So let's get started. First thing we have to do is actually start a PySpark session. So we'll say PySpark SQL import Spark session, and then I will create a Spark session. So we'll say Spark session, builder, app name, and I'll call this cluster, and then I will say get or create. So we will run that, and then I'm actually going to import our model. So we'll say from pyspark.ml, and we have to provide what family this belongs to, and in this case, this is a clustering algorithm. So from here, I can import K-means. Then we'll upload the dataset. The dataset, I've already downloaded it for you, and it's under the clustering folder under Spark for Machine Learning, but it's this kind of esoteric libsvm format. So we need to say spark read.format, libsvm, and then you'll say load, and it's called, you can just tab autocomplete this, sample k-means data.txt. So I will run that. The next thing I want to do is actually check out the data set. And this is kind of why it's a weird choice, given that we're doing k-means clustering, but if you show the data set, it's actually just this. It's 6 rows of data, and it has both a label and features. So I'm not sure if they're trying to imply that there's 6 different clusters to be expected here. The documentation example actually sets k equal to 2, so that's something that's a little bit peculiar. So just keep that in mind as we continue on throughout this project. What I really want to do is prove to you that it only needs features because this is an unsupervised learning algorithm. So I will say final data is equal to this data set, and I'm going to select only the features column. So I'm going to run that, and then I'm going to show you the final data. And the final data only has those features. So that's what we're going to be using, just to basically prove to you what a more realistic scenario would look like. And then I'm going to create my model. So we'll say k-means is equal to, and it's k-means, and then you can call off of this set k. And this is where you can set your k value. In this case, I'll follow along with the documentation. They set their k equal to 2. And then something else you can do is set a seed value. Now a seed value is just a seed value for a random number generator. So remember back in the theory lecture, where you actually start the centroids is randomly chosen. What you can do is set a seed number here. That way, in case you want to come back to this experiment and make sure you have the same quote-unquote random setting, that seed number is going to provide the same set of random numbers every time, as long as you have the same number here. So if you want to follow along with me and make sure you get the exact same results, set your seed equal to 1. So that's our k-means model. And now let's fit the model. So we'll say model is equal to k-means, and I'm going to fit it to that final data set. So now we run that. And while it's fitting, notice that it had no problems. So final data only contains features, and it has no problem fitting that because it's an unsupervised learning algorithm. If you try to do this on another data set, it would give you back an error saying it's looking for that label. So again, k-means only needs features, and you can even do shift tab here on this k-means, and notice that it only expects features call. It has no label column input. Okay, so let's continue on and actually try to evaluate our clustering algorithm. So something we can do is check out the within set sum of squared errors. So within set sum of squared errors, or WSSE, and then I will say that's equal to, and the way you do this is a little different than our evaluation metrics earlier, but what you do is you say model.computeCost, and then you pass in your data. So we compute the cost of our actual data set, and you're passing in the whole thing. You're not doing any test train splits. That doesn't make sense because we don't have labels. We're just kind of dealing with the entire data set as is, and then you can just print the within some squared errors, within set sum squared errors. So for us, it happens to be 0.119 repeating, and what we can actually do is check out the cluster centers. So if we look at our final data one more time and just show this, notice that we essentially had 3 dimensions of features. So we had this item in the tuple, this vector of items in the tuple, and then another one. And if we see here, the first one's actually empty or nothing on the first or the second 2 of the first row. So what we can end up doing is checking out the cluster centers, and because we know we have essentially 3 values in this tuple for the features, we should expect the centers to be in 3 dimensions. So in order to actually get the centers, we can say create a new object called centers and model dot, and it's going to be cluster centers, and this is a method, so you have close parentheses there. So if you end up typing out centers, it will return back the actual centers. In this case, it returns back 2 centers at 9.1, 9.1, 9.1, so this is like XYZ, and then another one at 0.1, 0.1, 0.1. So what does that actually mean? Well, it means since we set k equal to 2, it computed that the actual centers are at these locations. Now, generally speaking, especially if you're unfamiliar with the data set, it's a little hard to actually interpret the within set sum of squared errors, this number right here, or even the centers. I mean, we understand that this is some center in some 3-dimensional space, but truly what we want to know is if I look at my final data and say .show, I have essentially 5 rows. And what I really want to know is which group does each row belong to? Essentially, I want to know the label that I created for it. And the way you do that is you call your model, then say transform, and you actually then pass in the data. And again, we're not doing a test train split, which makes sense because this is unsupervised learning. We don't have any real labels to do the testing on, so we just have to pass in all the data during the fitting process, and we're going to pass in all the data during the transformation process. Because this is unsupervised learning, that's kind of part of the issues with it, that it's difficult to know for sure how well your model actually performed, because since the very beginning, we never knew the true label to compare it to. Now, there's definitely methods such as I mentioned the within set sum of squared errors to try to evaluate that, especially try to evaluate if you chose the right k. But let's run this now. So actually, let's set this as results. And then if I check out results, so notice now I can say show. And now I have the actual prediction. So this predicts that this is the first group. So these first 3 rows belong to the first group, and then these last 3 rows belong to the second group. Now let's run this again with a higher k value. So I'll set this k equal to 3, and now let's run this again. So we'll say KMeans is this, KMeans fit to the model, or the final data I should say, and if we compute the costs, now we get a different within set sum of squared errors, and it makes sense that it goes down as you increase k. Then we're going to check out the cluster centers, and note that we now have 3 cluster centers, and one of the clusters is slightly off the other one. So it looks like it took the 9.1 group from earlier and split it into 2, and it kept the other group the same. So now pay attention here. One of these groups should probably be remaining the same, and another group will be split. So we'll say results is model transform final data. We'll run that again. And what I'm going to do is check out the results. So remember this, first 3 were 1s, last 3 were 0s. If I run that again, well, look what happened. It looks like one of these groups stayed intact and it split off the other group. So now it has 2 0s and 1 2, which makes sense given that we saw one of the centers is essentially split off from each other. Okay. It's not always going to be that obvious, especially if you have higher dimensions, but in this case, the data was pretty simple with just 5 rows. Hopefully that makes sense. If you have any questions on that explanation, please feel free to post to the Q&A forums. Okay, so this was a really small data set. It was kind of strange in the fact that it provided labels for us already, but we really didn't need them. And what we're going to do is in the next lecture, look at a more realistic data set. In fact, it's a real data set from UC Irvine's machine learning repository. So let's get started. I will see you at the next lecture.